Time for our last video for 11.2, and this is going to be reading a computer output for a paired t-test. Suppose researchers wanted to know whether the use of cell phones impairs reaction times in a driving skills test. So reaction times in milliseconds are measured when subjects perform the driving task without using cell phones, that's sample 1, and then again with the same subjects using cell phones. So since it's the same subjects, that's why this is dependent, right? You're paired up with yourself. One time when you use a cell phone, one time when you don't. Before observations were taken for these two conditions, subjects had a warm-up time interval to become familiar with the task because they don't want them to do it cold because then that's not fair. And then I have the outputs for StatCrunch and Minitab. And of course, I wouldn't give you both on a test. And I might not even give you all the information I give you here on a test. I might take stuff away and make you figure it out because I'm mean like that. Okay, so how many people were sampled? That would be, it's kind of obvious, 32 right here. From StatCrunch, it's a little harder to see, but StatCrunch gives you degrees of freedom, so you can know that n is one more than that. So let me type that up. There we go. So again, if I gave you one, you should be able to find the other. I probably wouldn't give you both on a test. All right, when was the average time when not using a cell phone? Okay, not using a cell phone was group 1, right? Without using a cell phone, so that's sample 1. Now, StatCrunch is not giving you enough information to figure this out, so I'd have to get StatCrunch to give you more to figure it out. Minitab, however, gives it to you. Oh, let's see here. It's not using, so X bar. Let me type it up. Hold on. There we go. So again, this had to come from Minitab at this point because StatCrunch wasn't giving you enough. 534.6 is the mean, 66.4 was the standard deviation. Now, what was the mean for the difference? That's D bar. Okay, so, oops, pay no attention to that. That's my computer finishing up the last video. All right, so D bar, D, the little bar on his head, that was equal to the difference between them. And I think both programs gave that. It was negative 50.625. Double check myself. Yeah, negative 50.63, negative 50.625, somewhere in there. And then the standard deviation for the differences was SD, which was 52.49. Again, that was given in one of these outputs somewhere. Where is it? SD. Oh, there it is. 50.63, standard deviation 52.49. Right there. And now Minitab gave it, but StatCrunch did not. How could you find it with StatCrunch? Aha. Because that, of course, might be the kind of thing I'd give you on a test. So, well, the thing to keep in mind is that StatCrunch gave standard error. Standard error of the differences. And that's equal to SD over the square root of n. That's what we learned in Chapter 8. Okay, so it gave it to us that SE of the differences, standard error of the differences was 9.278. So you could put in 9.278 is equal to SD, which we don't know, over the square root of 32. And then you'd multiply both sides by the square root of 32. You'd make your calculator do it. If you do it over here, you got to do it over on the other side to keep things fair. Right? And then I would just make my computer do that, or my calculator. 9.278 times second square root 32. Enter. 52.49. Well, 48, but we've got a little bit of rounding error. So that's how you would find it by hand from what StatCrunch is giving it to you. Right? So squiggly equals 52.48. Okay? So again, if it wasn't given to you, because I might not, if I don't give it to you, if I give you the StatCrunch output, then you're going to have to find it yourself. I got to make a little space here. I got to get it to all fit on one page here. There we go. Okay, so I got it all fitting on there. All right, suppose a researcher wants to know whether the use of cell phones impairs reaction times. Which hypothesis are they referring to? Oh, okay, so we got to be careful about this. We were doing sample 1 is not using the cell phones. Sample 2 is using the cell phones, right? Okay, so let me type this up. There we go. So we want to know if, now it's going to impair your reaction time. So when you're not using your cell phone, driving through the slalom course or whatever it is should be faster, so lower in time than when you are using your cell phone. Because when you're using your cell phone, you're distracted, right? So it's going to take you longer to safely do the task. So not using the cell phone should be smaller time than using the cell phone. That means that if you subtracted using the cell phone from both sides, right, you'd get less than 0. And that means that mu d is less than 0. So there's your alternative hypothesis right there. Okay. So that means that we're doing this one in the middle right here. I'm going to highlight it with gray or something like that. That's the one. Maybe I'll give it a box. Okay. There, now I really punched it up. Okay, now the computer uses this notation. When you look at the computer notation, they've got up here mu1 minus mu2, mu1 minus u2 less than 0. Minitab's even harder to read. It's right there with that little parentheses where it says versus less than 0. It's letting you know that it's doing a left-tailed test. So why is that okay? Well, it's not really great, but we use D for difference of dependent groups. The computer programs are stopping at step 2 above. What they're doing is they're making this step right here what they're writing up, which isn't really great because dependent systems really shouldn't, well, not shouldn't, but I don't particularly like that method of doing it, but that's fine. You know, a computer program, they have to program it certain ways. And all they're doing is putting in the number 1 and the number 2 for grouping, or for using and not using, right? That's all. And using 1 and 2 in place of the group names. All right. Next. Now, what if we had reversed it? What if we had done sample 2 minus sample 1? How would that have changed your hypotheses? Well, it would have been the same thing, right? Except what sample 2 would have been backwards. So instead of doing what we subtracted using from both sides, we would subtract not using from both sides, right? So it would become, subtract this part over here away. So when you do that, you're going to get 0. You're going to get less than, and then you're going to get the mean of using over here, take away the mean of not using over here, right? Which would be 0 like this, mu 2 minus mu 1. Right? Because sample 2 minus sample 1. And of course, this is backwards. So who writes it that way? Nobody does, right? So we would flip it, and that would be this. And notice the alligator eats the mu part, right? Alligator's munching on the bigger thing. So if down here, I'm going to flip the sign and be this way. So the alligator's still munching on the bigger thing. And that would be the mu d is greater than 0. So it causes the inequality to flip, right? Switch sides, go from less than to greater than. All right, now let me find the test statistic and the p-value. They were in both of these outputs. Test statistic is negative 5.46 or so, and the p-value is, well, Minitab just says it's 0, which isn't really true, right? It's just the computer program gives up. Just like your calculators sometimes give up and just say 0, but it's not really 0. It's just really, really low. I like StatCrunch's way of writing this better. It's saying that it's less than 0.0001. It's something, but it's really small. Okay, so I'm going to go down here and I'm going to type those pieces up. Hold on. There we go. So is the p-value really 0? I just talked about that. So no, it's just really low, lower than 0.0001, and so Minitab gives up. And the calculators will do this too. Not as early as Minitab. Actually, it's, oddly enough, Minitab does it pretty much faster than anything else, but they will just kind of quit because computers can't run forever, so the people that program them to quit at a certain level. All right, so now we're going to have to draw a picture using the p-value method. Now notice this was a left-tailed test. So let me go grab that picture. I'll be right back. There we go. It's a left-tailed test. This is not at all accurate because, of course, 5.46 standard deviations is way off in the tail, like way off screen, actually. But that's okay. You get the general idea. It's a left-tailed test. You label that p-value. So is that statistically significant? Oopsie. Yes, it is for sure. So let me write that up. Yes. There we go. Because the p-value is, you could just say is 0.000 or is less than 0.0001, depending on what your computer gives you. That's less than 0.05, which was your alpha. So that means we're going to reject the null hypothesis, and that is the definition of what statistically significant is. Right? When you reject the null, that's significant, statistically speaking. Now, it's not necessarily practically significant, but it's statistically significant, meaning you had a p-value that was really low. So what conclusion would you reach? It's not going to be shocking for anybody, but there is sufficient or evidence or enough evidence to support the claim that, well, you could say cell phones increase driving reaction time. In other words, drivers get through the task more slowly when using cell phones. There we go. And we are all done with 11.2. I hope it was helpful, and I hope you learned something from it. Don't forget, when your p-value is low, that's when you reject, right? And if it's really, really low, the computers will just kind of quit on you and just say 0. I'll see you back here for more videos. But not for section 11.2, because we're done with section 11.2, thankfully.